morning, everyone. My name is Yongming Luo. I'm from Yongming University of Technology. So this is a joint work of Eindhoven, Delft, and Indiana University. So today we talk about regularities we find in the bisimulation reductions in big graphs. So what is bisimulation? Bisimulation partitioning is a very important notation and concept in many research fields. In database research, we use it for structural index, for XML data, RDL data, and also for graph reduction purposes. It can be seen as a way of clustering nodes together. For example, on the picture, we have 9 nodes, and they are grouped by this bisimulation relation. By applying this method, we can group them into 4 groups, and when we merge the edges between the groups together, we will have a smaller graph which will only have 4 nodes and 4 edges. So while doing this, we still preserve some kind of structural information of the graph. For example, reachability. So if we want to query that whether there is an edge between node 6 and node 8, from the abstract graph, the bisimulation graph, we see that there is no direct edge from between these 2 partitions. We can directly conclude that there is no such edge possible. So this is only one example of such query, but we can conclude that we can reduce the graph size while we still preserve some kind of structural properties. We call this abstract graph a partition block graph. So we are curious about what properties does this partition graph have. Alright, so the main question is, we know that for real-world graphs, power law distributions, this kind of regularity exists in in-degree and out-degree distributions. So, do this kind of regularities also exist in the isolation results of the the partition block graph? If it is true, how do we benefit from this kind of knowledge? So here's how we build up the experiment to investigate. So we experiment various kinds of graphs, from synthetic graph to real-world graph in the various domains such as social networks, also citation networks, and all the others. We use a state-of-the-art algorithm to compute the result. And in the following, we use cumulative distribution function to present the distributions. So the main result we find is that the power law distribution also exists in the partition block graph for real graphs. But this is not the case for synthetic graphs, for all the data generators we experiment with. So here's one of the results I showed you. This is the partition block size distribution for real graphs and the synthetic graphs. So as we see on the left hand, the real graphs, all the partition block size follow the power law distribution. For synthetic graphs, there are 4 data sets. One of them, the data set, only have 1 point on the plot. And as you can see, there's only maybe one, the SP2B data generator that has power law-like distribution. But even the SP2B fail on some other cases to be like power law distribution. So there's another example. We plot the in-degree distribution for the partition block graph. Again, for real graphs, they all follow the power law distribution. For synthetic graphs, many or most of them do not follow power law distribution. Okay, so here's the main update of my slide. So since we are here, I tested with social intelligence benchmark, which was the old benchmark from last year, and it was provided by TUC in the see. And I only generate, using the generator, a very small data set with 2.6 million nodes and 12 million edges. But I think even for this small data set, we can somehow see the structures the generator behave. So this is the in degree and out degree of the original graph. We see that for the in degree, it somehow is power law distribution follows, but for the out degree, it's not very much follow the power law distribution. So this is for the original graph. Then we go into the bisimulation results. So we see for the partition block size of the bisimulation result, it does follow the power law distribution. But for the signature length, well, signature is kind of the neighborhood information each node has. So it is closely related to the out degree of the original graph. So that is also not following power law distribution. We have two more graphs to show, which are the in degree and out degree of the partition block graph. So we see that the out degree of the partition block graph is kind of following power law distribution, but the in degree does not follow the power law distribution. Okay. So here are some insights you can draw from the small experiment. So we know that indeed for real world scenario, the power law distribution exists in the bisimulation results. So if we want to build up applications on this bisimulation results, we have to take that into consideration. So if we want to design or create structural indexes for such graphs, or if we want to do data partitioning based on this bisimulation relation, we have to think of this as a precondition. Then, I think it's obvious that some more work needs to be done for data generators if we want the graphs that the generators generate to be bisimulation friendly, to represent the real world graphs. We have to be a little bit more specific about this kind of thing. Then, well, this we do not cover in this talk, but we also examine how the bisimulation results grow when the original graph grows. We see that the bisimulation results grow at the same speed as the original graph, at least for one real world scenario. So here we test with the liquor data set. So that means if we want to build applications using the bisimulation results, we have to also consider the scalability problem, because if we want to build an index, the assumption usually is that you have the index in memory for the smaller graph, but this smaller graph can grow as well, so you have to use some techniques to make it smaller. For example, if you use different granularity for different parts of the graph to compute the bisimulation result, or you use different node labeling and edge labeling techniques to make the graph smaller. So that's what I have. I can show more.
You have fun.
So here I show a bit more plots. So these are the in degree distribution of the original graphs for the previous example. So again, you see clearly a power law distribution for real graphs and not so much for synthetic graphs. Out degree distribution as well. The signature length. So yeah, so this is just a
what the signature length mean?
The signature length is the kind of like the neighborhood information we have. That so so the signature means the neighborhood information, but we replace the outgoing nodes with the partition block they represent.
Mm-hmm.
So it's encoded neighborhood information.
Right.
Okay, so the algebra of the partition block graph. Alright, so yeah, this is the rest of the experiment I was talking about. So we tested with a flicker graph. The graph is growing from 17 million to 33 million edges. So we want to know, does the bisimulation result grow when the original graph grows? So the answer is yes. And how fast does it grow? It does linearly grow with respect to the original graph. So that's what we plan.
Okay.
Yeah.
Well, thanks. Other questions? I'm of course very interested in the LDBC things, but yeah.
So my question is, how fast is your bisimulation? I mean, for this real graph, how long time do you need?
So we test with various graphs. So for the biggest graph, we test this Twitter dataset. It's around 1.4 billion edges. And we have all kinds of algorithms to deal with that. So for the external memory version of the algorithm, it runs about a day on a single machine. So for cluster, if you use MapReduce algorithm, it runs around in 2 hours.
It's time for your egg.
For the others, they are much faster.
Okay. I have a question about can you bring back the social network benchmark or the early version of of it results? Because you mentioned that there were different results for the in and out degree.
You mean?
Because even though in the social network benchmark the friendship is directed, it is in fact symmetrical.
Yeah.
So it's not correct. I mean, if you are a friend with somebody, then the other one is also a friend with you, even though both of them are separately present. So I wonder how, I just don't understand how that in the out degree can be different.
So the graph I take is directly from the RDF graph it generates. I guess it has more information than the friend relationship.
Oh, so this is kind of everything thrown into the bucket. So you see here kind of an amalgamate of friendship with also both.
Yes.
Yeah, both and friendship, they behave very, very different.
So there's.
I'm very interested in the friends graph.
Okay.
So maybe we should.
Yeah, I think it's.
Yeah, so maybe just wondering how these are.
Right. Okay, so maybe, I mean, I'm really interested in your work and actually in also making a social network benchmark be realistic.
Yeah.
But this realism is most important for the friends part, I would say.
Okay. Yeah.
So can we then take certain, let's say that we have data sets that we want to test which are exerted from this social network benchmark in some way. And could we then, in what way could we apply these metrics? I mean, is the software available, or would we give you the data and you would run it, or what could be done?
It can be done either way. I can send you the code. It's no problem. Well, it's not online, but because the code itself is not very pretty. Yes. I can send you the code. You can send me the data set.
Yeah, it would be certainly interesting experiments to take certain thousand records and see how they interact.
Smaller graph data sets are pretty safe because I run this plus on simulation.